Kia ora koutou katoa and talofa. Welcome to this Resilience Challenge webinar looking at how volcanologists forecast eruptions in Aotearoa. Thank you for joining us in this May instalment of our monthly webinar series. I'll start with our karakia whiti ora and then I'll touch on a few housekeeping things before I hand over to the team. Ki mihi te pō, rangaha te ao, ki i o rangi, ki i o whenua. Kei nā mata o te ariki, kei mata nuku, kei mata rangi. Ki reira koe I tāne te waiora. Ko nā maungaru, ko nā awa parawhenua, heri uta ki tai, ki a tangaroa e. Ko koe, ko o, ko tāu I nei. Whiti ao, whiti ora. Ara mai te toki, humi e, hui e, tai ki e. Today we'll be hearing from Mel Whitehead and John Proctor from Massey University about how volcanic eruption forecasting is undertaken in Aotearoa. They'll run us through the feasibility of different methods, looking at forecasting parameters, warning times, and uncertainty. After the presentation, Jeff Kilger and Paul Viskovich from GNS and Mark Bebbington from Massey will join us for a panel discussion and Q&A. We'll use the chat function for our Q&A today, so please pop your questions into the chat as we go. The presentation should take about 30 minutes, leaving us another 30 minutes for Q&A and discussion. And with that, I will hand over to John and Mel.
Kia ora koutou. I'm John Proctor from Massey University, and I only have a brief comment to make at the beginning of the talk. And I have the privilege of leading and managing this research program. And the photo or the pictures you see there is the team of very experienced volcanologists across New Zealand that all come together to collaborate within this research program to basically figure out ways that we can provide better information around forecasting when our volcanoes become angry or when the behaviour of our volcanoes change that presents a danger or a hazard to us and our communities. So this is a real brief overview of our program, and this horrible diagram here sort of sums up our program. And our program of research is split into three main areas. The first area is about understanding the way that our volcanoes have changed over time and how we can build models to forecast what changes may occur in the future. The second part of the program in the middle of the slide there is really exploring new ways to simulate and model what may happen in the future as well. And the last part of the program is how do we communicate that science with stakeholders and actually take some of these complex models, which Mel's going to try and explain very clearly to everyone on how they work, and how do we use them for the community and for stakeholders. And that's a real brief overview of our research program. It's a collaboration of all researchers and most institutions across New Zealand to try and create some new tools on how we better forecast what may happen at our volcanoes. So I'm going to hand straight over to Mel. Thanks.
So hi, John, can you wave if you can hear me? Yes, great. So we're going to talk to you about how volcanologists forecast eruptions. So this is work done by the top 5 of these names. So you'll hear from me and John today, but it's also Mark and Max, also at Volcanic Risk Solutions at Massey, and Paul Viskovich at GNS. As we said at the beginning, Jeff Kilger is also here. He's a senior volcanologist at GNS. He's part of the wider RNC volcano team, and he is here today just for the panel bit to cover any questions you might have on the current GNS practices. So the stuff we're presenting today is based on these 2 papers. So this first one was by Mark and I last year, and it's just about how you choose your short-term forecasting method for eruptions. And then we applied this method to New Zealand, and this one was actually published yesterday, so it's hot off the press. So these are 2 papers that we're going to be talking around today. Before we get started, I thought it was worth making sure that we're all using the same words for the same things. So here we're going to use the word prediction as a definitive statement on future behaviour. We're going to use forecast to mean an uncertain statement on future behaviour. I might also use the word hindcast, which is producing a forecast but after the fact, so using hindsight. We are looking at short-term eruption forecasting, so we're looking on the hours to months kind of range. I'll use the word probabilistic, so that's the probability of an event occurring incorporating uncertainties, and we're looking at quantitative methods, so we're thinking of things that are measurable or numeric. Before we get into how volcanologists forecast eruptions, I thought it was worth thinking about, can we predict eruptions? So this is my 4-year-old and I on Ruapehu in January. And if you asked her when Ruapehu is going to erupt, she would have no trouble providing a prediction. For example, this volcano will erupt next Thursday. So this is a prediction because it's a definitive statement on a future event. My 4-year-old could also produce a forecast. For example, there might be an enormous eruption before I'm 4.5. This is a forecast because it's a statement on the future, but in uncertain terms. However, we're not interested in any forecast. So the question is really, can volcanologists accurately forecast eruptions? So to answer this semi-impartially, I've put together a series of quotes here from published works from the international volcanological community. So these two are from Steve Sparks. So forecasting is the central goal of volcanology, but in certain respects, volcanoes are inherently unpredictable. So even small factors can have large consequences. So we really have to talk about forecasting rather than predicting eruptions. These two are from Poland and Anderson. So despite progress, so this is 2020, despite progress, forecasting the onset of eruptions remains fraught with uncertainty, and it may never be possible to forecast every eruption. So this suggests that we will never be able to forecast all eruptions, but we might be able to forecast some of them. And these last two are from Marzocchi and Mark, who is here today, in 2012. And they look at this problem a bit more technically. So there's a practical impossibility of predicting, even with a small uncertainty, the onset time, location, and size of the impending eruption. And while uncertainties cannot be completely eliminated, they can be reduced through the development of more reliable forecasting models. So this work is essentially both of the previous two. So we can't predict eruptions, but we can maybe forecast them. And to do this, we need to produce better models. So can volcanologists accurately forecast eruptions? Probably not reliably or universally, but we're working on it. So now hopefully you have an idea of the current sentiment around eruption forecasting. We'll get into the nitty-gritty of things. So the problem of eruption forecasting can be viewed like this. So we have some questions. So when and how will this volcano erupt? And to answer this question, we have some information. And this is usually a combination of knowledge and data, and it can be general or it can be volcano specific. So general information includes things like scientific principles, so the laws of motion, gravity, thermodynamics, as well as various databases, so eruption databases, or those that include global monitoring signals. But then for your volcano of interest, you have some volcano-specific data, so any eruption history, literature specific to your volcano, and any past and current monitoring data at or near your volcano. But to get from this information to the question of forecasts, you need to interpret the information. So what do these things mean? And then you need to extrapolate this information. So what do these things mean about the future? And to do this, to get there, you need a set of assumptions. And these assumptions are usually folded into a model or a method, and it's these that we are talking about today. So today we're going to describe 6 forecasting method types alongside some specific examples. The important bit of this slide is these 2 assumptions at the bottom. So all forecasting methods adopt these 2. The first one is that what happened in the past tells us something about what happens in the future. For example, the size of previous eruptions at a volcano might give us clues as to the next eruption size. And assumption 2 is that data that can be observed is in some way related to the forecast. For example, we see increasing seismic activity at Ruapehu. We assume that this is in some way related to determining when and how Ruapehu will erupt. So these 2 assumptions are used by all of the forecasting methods. We just need to cover one more point before we get into the methods, and that is of eruption parameters. So when will a volcano erupt is kind of a straightforward concept. So we're looking for like a date or a time to an eruption. How will a volcano erupt can be defined in many different ways. We're just going to show you 5 options, but then many more exist. So the second one, they're going to appear on this list down here on the left. So the second one is where a volcano might erupt. For example, in my little picture here, an eruption at location A might be less worrying than an eruption at location B, which is near population or infrastructure. In New Zealand, at the Auckland volcanic field, eruption location is vital to constrain the hazard footprint for evacuation. So that's location. We're also often interested in how big the eruption might be. The eruption style, so is it explosive or effusive? Or commonly the volcanic explosivity index is used, the VEI. So this is a measure of the explosiveness of an eruption. So a larger VEI is more explosive. So in general, VEI 0 is non-explosive, so runny. VEI 8 is Yellowstone caldera or Taupo's Oaranui eruption. Often when the eruption might start is just not enough information. So we want to know how long this first phase, this first bit is going to last. So is it like one bang and then it's done? Is it going to be a day? Is it going to be a week? Or are we talking on the scale of months to years? And this is important for evacuation decisions, but also when it's safe to send in search and rescue teams or safe to return. And if you're displaced from your homes and livelihoods for months to years, this is very different problem than spending a day or two in an evacuation centre or if you're sheltering in place. And the last eruption parameter that we're looking at today is what hazards are more likely to occur during this next forecasted eruption. So this is important because the impacts, say, of widespread ashfall are very different to volcanic gases or lava or debris flow. And there's also no reason you'd only get one hazard per eruption bit. So you can see here that I've used two images from the 1991 Pinatubo eruption, so that ashfall picture and the Laha one from the same eruption. So now we have our set of eruption parameters that we are interested in forecasting, so we can start looking at which methods might be able to forecast which parameters. So this is how each method will be presented. So the eruption parameters we just talked about on the left, the requirements are on the right, so the things you need, and then the method is in the middle. So if a parameter or requirement is highlighted, this means that it's always or almost always the case. And if there's that little yellow star next to a requirement, this means that it'll be used if it's available. So hopefully you'll get the idea as we go through. So method one is expert interpretation. So some monitoring data comes in, an expert, or more usually a group of experts, look at these data and they produce a forecast in real time. So there is two distinct advantages of this method that you can see via the highlighted bits. So the only thing you need, the only requirement to produce this forecast is of expert personnel, and this method can produce a forecast for any of these eruption parameters. So those little stars there mean that even though you can run this forecasting method just with expert personnel, if there is monitoring data available or previous monitoring and eruption data, these experts are going to use that during their forecast. So they would use these if they're available. The main limitations with expert interpretation are that experts are inherently subjective. So any forecast produced is expert dependent. And during heightened volcanic unrest, they're just operating under suboptimal conditions. So it's high stress and short time constraints. As we go through these methods, I'm going to list the assumptions on the bottom left of the slide. I won't be reading through them because I can be pretty sure that I'm the only person here who thinks the assumptions are the most exciting bit, but they are important. And if you're going to use the output of any of these forecast methods, you need to consider how valid these assumptions are. So that's expert interpretation, method one. Method two is event trees. So an event tree uses an algorithm to produce a forecast from this kind of predetermined structure of nodes and branches, these dots and lines in the picture. You travel from left to right, linking events to subsequent events, and then you update your forecast by moving along the tree using monitoring data and real-time expert interpretation. There's also Bayesian event trees that have starting estimates, so underlying prior distributions. And these are usually built from existing knowledge and previous monitoring and eruption data, and these are updated as they come in. So in my picture that I've drawn for you today, you see this magmatic intrusion on the left. This might lead to no eruption, or it might lead to an eruption. If there is an eruption, you might want to know how explosive it's going to be. So it'll be VEI 0, 1, 2, 3 in this picture. And then for each of these VEIs, you have a forecast as to the probability of each of these hazards occurring. So compared to real-time expert interpretation, event trees can be constructed in advance. So when everyone is available and there's plenty of time to have a good chat about everything. The main limitation with this method and with the next one that I'm going to talk about, belief networks, is that they do not directly forecast eruption onset time. So instead you get a forecast of a specified, it's called a look forward period. So it's usually about 2 weeks. So you just get the forecast for things that they think might happen in the next 2 weeks. So I've got an example here for you. So if you want to know more about event trees or you're interested in event trees, I thoroughly recommend reading this paper because they have all the event trees that they used in real time, for this eruption at Agung, and they have provided all of them and the reasons for why they changed their forecasts in real time, and they're all run in Excel. So you probably already have the software on your computer to run this forecasting method. So event trees look kind of pretty similar across the board, almost template-like. So this one, the one that I'm showing you is for the look forward period of 2 weeks from the 23rd of January 2018. So an eruption was already in progress. So you can see that node on the far left says eruption, and it has 100%. So you estimate the chance that the eruption stops, so that's at the bottom, or continues, or the middle, or escalates, so that's the top one. If it escalates, you then want to estimate an estimate of what it might escalate to. So you can see that they branched into VEI 2, 3, and 4 to 5. And then for each of these, there's an estimated probability of each hazard occurring. So that's this in this events column. And then they provided an estimate of what distance they think this hazard might reach. So that's event trees. Belief networks. Belief networks are like a free-form version of event trees. So experts design the kind of conceptual setup, so what they think is happening in the subsurface, and how they think these things are linked to what they can see, so the observations, the monitoring data, and how they think these things in the subsurface are linked to eruptions. So it's kind of a network of interrelated beliefs that you put probabilities to. So in this example that I've drawn for you, there's a belief that magmatic intrusion is linked in some way to effusive and explosive eruptions, but also might be linked to detections of degassing, seismicity, or inflation, so those green nodes. Because these are more abstract, more complex than event trees, a training step is often used to kind of set the probabilities up through the system. But if you want to do this training step, you need previous eruption and monitoring data. So you can only train it if those data exist. The main limitation for belief networks, like I said for event trees, is that doesn't directly predict eruption start time. And as I said before, if you want to train it, you need this previous eruption and monitoring data. That's belief networks. This is an example. This is from Hinks et al. In 2014. So they built this belief network after the fact, so after the 75-77 eruption at La Soufrière. And they created it to get a better handle of what might have been going on in the subsurface and how it was linked to the eruptions that they saw and the observations that they could see. So you can see that little dot in the middle is magma intrusion. So magma intrusion is somehow linked to some deep source ground deformation. And from this, they think they might have observed some borehole and dry tilt meter movements. These green ones are the real-time measurements. So you observe your green nodes, and this information is sent back through the system through these arcs and your white kind of conceptual nodes to get your eruption probabilities. So there's a point maybe worth mentioning here, and that is belief networks and event trees still rely quite heavily on experts to build these conceptual models of the subsurface and to populate the probabilities along the tree or the network. But the bonus is, like I mentioned before, is that these can be developed during quiescence, so when everyone is calm. Method 4. Method 4 is the failure forecast method. So it forecasts eruption start time using an accelerating signal to estimate the future time of failure. So you find a signal that's accelerating. This could be inflation or gas concentration or the number of earthquakes per day. And then you choose a time where you think the signal started accelerating, and then you fit a curve to the signal. And when this reaches an asymptote, so when it reaches infinite acceleration, this vertical red line in the picture, that's your failure forecast time. As an aside, if you're interested in assumption lists, this is a good one to start with, but I digress. Currently, you only get a forecast of eruption start time from this method. The choice of where you think your signal starts accelerating is also really important because it will affect the curve fitting step and ultimately the forecast. But the main practical limitation with this method is that when you're running it in real time, you must observe this accelerating signal. So there's lots of work that's been presented showing this approach after the fact. So when there's plenty of time to look around and find your accelerating signal or to manipulate the data until it resembles one. But in real time, there's just no guarantee that the method will be able to produce a forecast because you can't be sure that a specific monitoring station will see this accelerating signal, even if one has been seen there before. So here's our example. This is an example at Villarrica, Chile, for the hindcasting of 2 explosions. So after the fact, they went back and looked at the data, see if they could have forecast it. So the data they used are seismic. So more technically, they used this 1/over normalized R sound, which is real-time seismic amplitude measurement. I've just put that in because that 1/over means that now we're looking for where the line crosses the y=0 axis. So that's the forecast time. So the 2 explosions were on the 26th and the 28th of October, where I put those little volcano pictures. The black dots are the data points, so it's measured over every 10 minutes. And then the red lines are what they fitted to hindcast the explosions. And you can get an idea from these red lines as to the problem of choosing where your data starts accelerating. So they essentially have 2 accelerating signals here that overlap. So it's just really hard to see how you'd have done this in real time. The authors also state in the paper that this method might not have been useful for other eruptions at the same volcano. So that's failure forecasting. Method 5 is process source models. So these are still mainly conceptual. They're based on a predetermined model of the subsurface from which specific signals or sets of signals are expected. And then as you observe the signals moving through your system, you update your forecast. So I'm going to be showing you stuff around seismic signals, but there's no reason you couldn't do it with any other observations. And ideally, you would use as many observations as you have all in the same model. So because most of them are currently based on hypercenter locations, or at least earthquake depths, to estimate where the magma is currently located, to run these, you need a decent number of seismic stations. And you need your experts to construct this conceptual model during your method building phase. The main limitation is it's still conceptual, but this one I think is better understood through this example. So here you go. This is a process source model from McCausland in 2019. So it's still conceptual. So they used it for the Cinnabung eruption in 2013, but they used it to aid the event tree forecasts for Cinnabung. So it wasn't used directly for the forecast. So this model has 4 stages for this example. So you build your own one for your own volcano. This first stage is deep seismicity. So they say, when we observe deep seismicity, this means that magma is rising from a lower crustal storage region. And this goes all the way up to the 4th and final stage, where the observations of repetitive seismicity suggest the final ascent of magma to the surface. So this is my favorite method because you could theoretically combine all of your knowledge and all of your data into one big, almost kind of systems model. The problem is that it's still in the conceptual stage, so it's just not ready yet. And the last method we're looking at is machine learning. So this is method 6. So machine learning used past data to train an algorithm so that it knows what to look for. And then as new data comes in, you look for these predetermined sets of patterns to produce your forecast. Machine learning eruption forecasting so far has relied on classified methods. These are called supervised methods. And this is because you're interested usually in a specific classification, i.e., will the volcano erupt? And then your classifiers are yes or no. All of the other models we've talked about use knowledge in some form to construct their forecasts. Because machine learning methods learn entirely from the data, you just need a lot of data to train them. So the recommendation from this machine learning and volcanology book is more than 50 events per classification. So say we are interested in determining whether a signal means an eruption or no eruption, Then we need data related to 50 eruptions and data related to 50 times where there weren't eruptions. And while the recommendation is 50, for most of the volcano seismic classification applications, so not forecasting, but just kind of working out where seismic signals go, they use a lot more. So I put an example in here where they use 800 events per class, and they run the whole thing 50 times with different training and test data to make sure that their results are statistically robust. So when I was writing this, it's quite hard to kind of visualize machine learning, I think. So I thought I would just show you what it looks like when it runs on my computer. So this is just a screenshot. So this is the method of Dempsey et al. For Fukari. So it's retrospective method. So it was used for Fukari. It was produced after the December 2019 eruption. It works on a look forward time window, so where you get an alarm for eruption, yes or no, and it's based on exceeding some threshold probability. So when you run it on your computer, you just see this little black command line box where the code is run. The large window is the main script, so you might be able to see, depending on how big your screen is, a model called forecast now. The window on the right is the function that pulls the current data from WIS, so that's this little seismometer on the southeast of Fukari. And the little box in the middle is the classification information that they used. So they used these 5 eruption start times and the data from WIS, the seismometer, to build the forecast. I should say none of this code is mine, but if you want to download it and have a little play, you can find it on this GitHub page, on Dave Dempsey's GitHub page. It's all open source. So now you've had a whirlwind tour of how volcanologists forecast eruptions. Hopefully kind of getting the impression that it's not a question of what method we want to choose or what we feel like on the day. It's a question of which methods can we responsibly choose. So we need to know what these requirements are met at our volcano. We need to think about what we need to know for our volcano, and then those 2 things inform which forecasting methods, or maybe you need a few, are feasible to get the parameters that you want. So we applied this approach to all of the 12 volcanoes currently monitored through GeoNet, but we're just going to present 3 today. This is mainly for our collective sanity, but we have the slides with us for all of the other ones in case I don't talk about your favorite volcano, but they're also in that second paper, that NZJGG paper. Volcano 1, the Auckland Volcanic Field. So for each of the 12 volcanoes, we looked at the level of effort required to estimate each of the 6 forecasting parameters with each of the forecasting methods. So you see where it says eruption onset time, that column there, those are our parameters, and then along the top, on the side, are our forecasting methods. You might see that there's 7 methods here, and that's because I've split that belief network into belief networks that are based entirely on expert elicitation and belief networks with that recommended training step. And then the colours in these represent the perceived level of effort. For example, you see that first blue column under expert interpretation. So there's negligible effort, so blue, required to estimate any of the eruption parameters using expert interpretation. But there's significant effort, so red, required to estimate eruption onset time using this belief network. This is the AVF. There are more than 50 eruptive centres, so those red triangles. Distributed over an area of 300 square kilometres. It's already a Bayesian event tree constructed by Jan in 2010, but more recently updated by Alec Wild's PhD. The data collected during these formal expert elicitations could be used to inform belief networks. It is a distributed system, which means that accurate hypercenter location or the observation of the accelerating signal will just be really tricky. And there's no monitoring data from any of the past eruptions. The most recent eruption at Rangitoto was about 500 years before seismometers were installed in New Zealand. So machine learning methods are out. Ruapehu next. You can see from the map there's a 20-kilometre ring that we used to determine which monitoring equipment to count, but this is just so that you kind of get an approximate idea of how many are nearby. So I put this larger map in because the proximity to Ngauruhoe and Tongariro means there's a lot of extra signal options around, so no methods get ruled out or in because of this 20-kilometre ring. So you can see, because there's no black on this chart, that at Ruapehu every method is deemed plausible, just to some different degrees of effort. And this is useful information because if we need a New Zealand volcano to develop and test forecasting models for, Ruapehu looks like a good candidate. There are about 12 eruptions that have occurred at Ruapehu when monitoring equipment has been in place, but only 4 of these are covered by digital seismic records. And that's just really not enough to train machine learning algorithms. But I will return to this point in a few slides because our last volcano is Whakaari. So at Whakaari, there are 2 broadband seismometers installed, but you can see from this image that that northwest one isn't currently operational. Similarly to Ruapehu, there are quite a lot of eruptions that have occurred while monitoring equipment has been in place, but most of these need to be vectorized from paper seismograms. And that machine learning algorithm from Dempsey that I showed you before is currently undergoing testing. So these are all the volcanoes together. I don't expect you to be able to take all this information in, but it gives you an idea of which volcanoes are most promising to develop forecasting methods at. So the ones that don't have any black on, so Ngauruhoe, Ruapehu, Whakaari. And the consistent blues for the expert interpretation, those columns, the first column for each one, but for no other method, shows you that expert interpretation is the only method available in New Zealand for any forecast parameters at any of our volcanoes. But to get some of the more exciting forecast methods running, so machine learning or belief networks with that training step, we just need some more data. So I wanted to show you quickly what data are out there in paper form so that we're not all completely depressed at the end. So here we go. So these images come directly from Paul Viskovich at GNS. He's here today if you have any questions on these older seismograms. So this is from September 1995 eruption at Ruapehu. These ones are from Ngauruhoe in the 1970s. And this image shows you how much data are kind of available but hidden away in these old seismograms. So the green that you're looking at is the time period covered by digital records. So those are the ones that we have access to now. The grey is the paper, and then the blue is the film. So if it's just a triangle, these represent eruption time. So short instantaneous eruptions are just a triangle, but longer eruptions are those 2 triangles with the dashes in between. So if you look at, say, Whakaari or Ruapehu, we can see that there's loads of eruptions in there that we have temporally aligned monitoring data for. They're just not ready. They're not in a state yet to be interpreted by these data forecasting methods. So the point of this slide is that all is not lost. This is just a slide to show you the process as a whole. So there's methods in the middle, forecasting outputs on the right, requirements on the left. So you just follow the lines for whichever requirements you need and whatever outputs you want. And now we're coming towards the end. So hopefully you now have a better idea of how volcanologists forecast eruptions. The main message that we're trying to get across here is that before you use a forecast, you need to think about whether the data and knowledge requirements can be met, whether a method can forecast the parameters that you need, how valid the assumptions are for your specific application, and how limiting the limitations will be for what you want to do with your forecast. So our general hope is that we strive to develop as many methods as possible for each volcano. And I put a little disclaimer in here that links back to my 4-year-old's forecast earlier. So we've looked here only at the practicalities around what and how you can forecast eruptions. There is no implied assumption that those that are easiest to apply will provide the most accurate estimates, or which of these are more likely to be trusted during an actual volcanic crisis. So I'm handing back to John here for some concluding remarks, and then we will open up for discussion. Thanks.
Kia ora, thanks, Mel. I mean, thanks for the brilliant presentation covering all these models. And really just to add a final comment, you know, we have the capabilities in New Zealand and the ability to apply some of these models, these tools to our volcanoes. But in applying those tools, we have to be very careful on how we apply them and operationalize them, and then work with stakeholders in the public to then make sure that they become a standard tool that's then used in our hazard management going forward as well. So there's a lot more work to do around how we actually develop these tools in a real world situation and apply them in New Zealand as well. And that's the final comment from me. So we can open it up, hand it back to Delia and open it up to questions.
I think she left.
No, I'm still here. Have a look in the chat, John?
The chat, sorry, yeah, we haven't been monitoring the chat.
That's where the questions are going.
Okay. So Mel, there's a question there from Michael Drayton.
So do volcanoes elsewhere in the world inform our knowledge of New Zealand eruption forecasting, or is every volcano unique? That's a great question. If you are super interested, there's an awesome paper by Cashman and Biggs in 2014. And it's about common processes at unique volcanoes. So there's a lot of work that is on analog volcano using analog data. So that's using data from other places to inform your forecast. But there's just loads of problems remaining about how you choose which volcanoes are more like yours, and how best to use your data and when it's useful. So hopefully that answers that. Craig Miller wants to know, uncertainty is important. How do you capture that in forecasts? Yes, it is super important. That's my most favorite thing, is uncertainty. It is captured in a lot of these forecasts, but so maybe Mark would like to talk about epistemic and aleatoric uncertainty. It's his favorite topic.
Yeah, I can make a comment on that. Some of the models don't produce uncertainty, and some of them do not quantify uncertainty, and that's a further level it goes on. But basically, the whole thing is uncertain, and it's uncertain as to when it occurs, if it occurs, what it occurs. And yeah, this comes into Michael's question as well. How much we can actually leverage analog volcanoes to help improve our understanding and hence reduce our epistemic uncertainty, which is the problem that the volcano may not be thinking the way we are.
Thanks, Mark. So the next one is, yes, source process models are currently my favorite. I just feel like they are the ones that can best incorporate all of our knowledge and all of our data in the most useful way. But I mean, I'm sure everyone has their own favorite model. So yeah.
Could the source process models also incorporate some of the other models to remove some uncertainty?
Yeah, and they can definitely inform them, like they use them already at Cinnabung. So I think it's just because I'm an engineer and I like the kind of idea of it becoming a systems model eventually. And I think that we do know quite a lot about all these volcanoes, and I just don't know if we're capturing all of that knowledge yet into these forecasts.
Oh, there's 2 more questions there, Mel. 3.
Can we forecast the amount of ash that may be expected from different eruptions? Yes, we can forecast it. Can we forecast it accurately? I don't know.
I think this is that's a really tough question, because we're moving away from forecasting those parameters that Mel was talking about to actually then simulating a real world event. So there's a difference between forecasting and then simulating what may happen as well, and simulating physical impacts or geophysical processes. And so that's another part of the, I suppose, challenge program. That we're also doing research around building better simulation tools and then simulating some of those impacts.
Next one is Graham Leonard on WOVADAT. So WOVADAT is volcano observatories, and they all have these links to their monitoring and eruption data. So I think that comes back to what Mark was saying before about analog data. It is super useful. So we have a PhD student actually at the moment who might be here, and she's looking at these data and how they might be linked in a kind of informative for our problem way. So yeah, don't know. Do you want to add anything to that one, Mark?
Yeah, part of the problem is that WOVADAT's only had qualified buy-in, shall we say. There's a lot of countries which are not well represented. And once you get that, there is a massive problem with trying to reduce the information to something which you can model, because you have types of seismograms, you have observation and non-observation periods, you have all sorts. Every volcano has a unique monitoring system, and somehow you've got to homogenize this. So somebody who's starting their career, there's a great place to start.
Next question is ensemble forecasting. Yes, I think that is a great way to go. So that's how they do it now. So I used to work in the geophysics department at Edinburgh, and they do seismic imaging of oil fields. And what they do is they have 4 completely different algorithms, and they run it, and then they say, do they all agree for if there's oil there and stuff? So I think definitely ensemble forecasting is a great way to go, or at least developing as many methods that we can responsibly develop for each of these, so that people can look at what each of the outputs are to get an idea of the uncertainty space. Craig Miller, yes, I completely agree. I think source process models are intrinsic to expert judgment. So like John was saying before, if we can combine them in some way, that's probably the good way to go. Sarah asks, how long do you think it'll be before we can get a warning forecast, like a rain warning? I don't know.
Do you want me to have a well?
I'll talk about rain first. So the bonus with weather forecasting is that there's always a feedback loop. So you can make a forecast about how much rain there's going to be tomorrow, and then the next day comes, and then you already have like some feedback, so you can improve your models, and you're always getting, how good is this model? Is it, how well is it doing? We just don't get that until a volcano erupts. So go on then, John, be more holistic.
That's a really good question. And I think, as we said at the end of the presentation, we have these tools and capabilities to be able to run these models, but we have to think of the ethics around applying them and then communicating them to the public, and then using them as a standard tool within emergency management. There's still a lot of work and research to go around on how we effectively communicate the outputs of these tools. And I think we need to be very careful with phenomena such as volcanoes on the way that we communicate our information to the public to then make decisions to make their community safer.
So next question is, when you have more than one viable forecasting model for a volcano and run them, how commonly do they generate significantly different forecasts? I don't know, because very rarely do people actually run them in real time and show you the forecast all the time, but that would be a great PhD. The question of belief is different, and I think that's important also. John, you want to talk about beliefs?
Beliefs, yep. So the next one, is there any scientific merit to data source from human stories prior to actual recorded events, and do we take any of this into account at all with any of these methods, since it would be so difficult to quantify? That's a really good question, and there's probably no reason why we can't incorporate some local knowledge or even Indigenous knowledge into some of these forecasting tools and build models around those as well. And currently, I would say that there is a certain amount of local knowledge that goes into some of our expert interpretations or expert elicitation models as well. So it's not impossible to do. It is sort of occurring informally at times as well. And it would be nice to see if we could formalize that and merge those two worlds, I suppose, to come up with a really good output for our locals, for local solutions around our volcanoes.
Great. Next question is, do you relate earthquakes on the, I don't know how to say that word, Hikurangi subduction zone to volcanic activity? The answer is I don't, but Jeff is here. Jeff, do you relate these things?
Right, you really throw me a good one there.
I wasn't waiting for a good one for you. There you go.
So there's some evidence that suggests that slow slip events, which are off the around the subduction interface on the east coast, that's transferring stress onto the volcanic systems. So we've seen some evidence that there's been some deformation changes and possibly earthquakes associated with topal caldera during these events. But more specifically on large earthquakes, there's some building evidence which would indicate that if a volcano is close to being ready to erupt, and that dynamic stress transfer onto those volcanic systems can tip the magma into an eruption. And so it is plausible that a very large earthquake occurring off the east coast or in the Hikurangi subduction zone could set off an eruption if it was in the right space to do so. It wouldn't necessarily kick a volcano into action that wasn't already close to being ready.
Thanks, Jeff. The next two, they're going to be yours, John.
So there's two good questions from Christy Lee and Wendy.
Yeah.
And yeah, I think there's no reason why we can't bring in Indigenous knowledge and local knowledge into some of these methods and test them. I suppose in terms of expert elicitation, I would say that iwi, hapu and whānau probably living around volcanoes use their own expert judgment in their day-to-day lives anyway when managing their activities around working around those volcanoes. And so understanding the way that they make decisions and then apply those decisions would be a really useful exercise.
So the next question is, can you comment on the way forward for dealing with large caldera systems where there aren't really any global analogues for unrest leading to large eruptions? I'd say this is a problem not just for the large ones, although maybe exemplified in the large ones. I don't know what the way forward is. I guess developing more conceptual models, getting a better understanding of what is going on in the subsurface. Some of those forecasting models, you could produce a forecast even without this analog or monitoring data. John, you have a thought?
No.
You look thoughtful.
I was just reading the question, sorry.
Oh, Mark has a thought.
Yeah, the leaders here are the Italians with Campoflegre. They've had a very, very long running and detailed expert elicitation process going on to inform an event-tree model there. So in as much as no one's actually got any observations apart from a small, the Monte Nuovo eruption in 1536, I think is the only observed one we're talking about. And you should go to Aotearoa with the Tarawera eruption, which feeds back to John's comment on Indigenous knowledge, etc.
Thanks. The next one's from Alberto. Oh, yeah, using transfer learning now. That'll be cool. Send us the paper when it's done. Craig thinks the Bayesian network is suitable for incorporating meta. Yeah, no, I agree with that too, I think.
Yeah, I think that it is something we've talked about, but I mean, we have to be very careful in the way we or the ethics around incorporating knowledge from other cultures into these models as well. So we have to be doing this under strict kaupapa Māori methods and in a proper partnership that applies co-design and working in that complete partnership to do that.
I think that's it. We've run out of questions. We should have done a poll on favourite methods, but that's all right. Delia?
Yes, thank you. Well, we are doing a post webinar feedback survey, Mel, so we could put a poll in there for you if you like. Since there are no more questions, I'll wrap up. Thank you to our speakers and panelists for sharing their time and research with us today. Hopefully you found this interesting. We'll email a video link to you all soon, along with that short feedback survey. And if you've missed any of our previous webinars that you're interested in catching, they're all on our YouTube channel and you can just Google to find them. A big ngā mihi nui to you all for attending. We hope you enjoyed this, and do look out for our next webinar in June on precarious livelihoods and disaster resilience. Are we getting heaps more questions now? No, we're not. And that will be presented by our Resilience and Practice program in June. And with that, kia pai tō rā and manuia le aso.